exponential functions, base greater than 1. Base greater than 1 already, because if a is greater than 1, then the graph of f of x, a power x grows taller as it moves to the right. To see this, let n belongs to the element of z. We know that 1 is less than a, and we know from our rules in inequalities that we can multiply both sides of this inequality by positive number. The positive number will be multiplied by a power n, so that we will have a power n into 1 equal to 1 less than a power n a power n of 1 less than a power n into a. That is, here base is 1. That is, we can say here a power n equal to into 1 equal to a power n only. But a power n a equal to n, here base is the same. That's why a here is a power 1. That's why n plus 1, a power n plus 1. The inequality above is the same as a power n is less than a power n plus 1, because the last inequality we found is true for any n elements of z. We actually have an entire string inequality less than minus a3 minus a power minus 3, a power minus 2, a power minus 1, a power 0, a power 1 up to a power 3. Keeping in mind that a power x is positive for any number. A power x is positive for any number x, and that a power 0 equal to 1. We now have a pretty good idea of what the graph of f of x equal to a power of x is. Looks like if a is greater than 1, y intercept is at 1. When moving to the right, the graph grows taller and taller. When moving to the left, the graph becomes shorter. That means moving right taller from x-axis. Okay. From moving left, lower than lower, shorter than shorter, swinging towards, but never touching the x-axis, but never touching the, not like that, only not touching. Okay, not touching. Not touching, never touching the x-axis. Not only does the graph grow bigger as it moves to the right, but it gets big in hurry. For example, if you look at the exponential function whose base is 2, then f of 64 equal to 2 power 64, then 18, 446, 744, 073, 709, 525, 000, 3 times 0. And 2 isn't even a very big number to be using for base. Any positive number can be base, and plenty of numbers are much bigger than 2. The bigger the base of an exponential function, the faster its graph grows as it moves to the right. Moves to the right. Here also already mentioned f of x equal to a power x. If a is greater than 1 only, here is less than shorter the a power x. Then if greater than 1, then going up longer, taller. Okay. Moving to the left, the graph f of x equal to a power x grows small very quickly if a power a is greater than 1. Again, if you look at the exponential function whose base is 2, then f of minus 10 equal to 2 power minus 10, equal to 1 by 2 power 10, equal to 1024. The bigger the base, the faster the graph of an exponential function sinks that as it moves to the left. Base less than 1 but still positive. If a is positive and a less than 1, then we can show from our rules of inequalities that a power n plus 1 is less than a power n for any n the element of z. That means that here we have seen less than, here greater than a power minus 3 less than 1, a power minus 3 greater than a power minus 2 greater than a power minus 1, a greater than a power 0 greater than a power 1 greater than a power 2 greater than a power 3 and so on. So the graph of f of x is equal to a power x. When the base is smaller than 1, slopes down as it moves to the right, but it is always positive. As it moves to the left, the graph grows tall very quickly. Here 0 to 1 to 3, minus 3 minus 2 minus 1, what we have seen, that's one. F of x to a power x. If 0 is less than 1, a is sorry, 0 is less than a is less than 1. A power minus 1, a power minus 2, a power minus 3, 1, a power square, a square, a plus, so 1 to 1 and on to. Recall that an exponential function f is a function from r to 0 comma infinity. F is function from r to 0 comma infinity as it domains that set r and has its target to set 0 comma 8 0 comma infinity. Function f is a function from r to 0 comma infinity. We see from the graph f of x equal to a for x. If either a is greater than 1 or 0, a is in between 0 to 1. That is a is less than 1, a is less than, sorry, 0 is less than a and a is less than 1. That is f of x is 1 to 1 and on to. Remember that to check if f of x is 1 to 1, we can use the horizontal line test which f of x passes to check what the range of f of x is within of compressing the graph of f of x onto the y axis. If we did that, we would see that the range of f of x is the set of positive numbers 0 infinity 0 comma infinity. Since the range is and the target of f of x are the same set of f of x is on where exponential function appears. Exponential functions are closely related to geometric sequence. They appear whenever you are multiplying by the same number over and over and over again. The most common example is in population growth. If a population of a group increases by say 5% every year, then every year the total population is multiplied by 105%. 105%. That is, after 1 year, the population is 1.0 times what is originally was. After the second year, the population will be 1.05 whole square times what it is originally was. After 100 years, the population will be 1.05 whole 100 power 100 times what it is it originally was. After x years, the population will be 1.05 power x times what it is originally was. Interest rate on credit cards measure the population growth of sorts. If your credit card charges you 20% interest every year, then after 5 years of making payments, you will owe 1.25 power 5 equal to 2.48 832 times what you originally charged on your credit card. After X years, after making payments, you will owe 1.20 X times what you originally charged. Sometimes the quantity decreases exponentially over time. The process is called exponential decay. If a tree dies to become wood, the amount of carbon in it decreases by a 0.0121 every year. Scientists measure how much carbon is in something that died and they use the exponential function f of x 0.999879 power x to figure out when it must have died. The number of 0.999879 is the best base of this exponential function because 0.999879 is 1 minus 0.00121. This technique is called carbon dating and it can tell us about history. For example, if scientists discover that the wood used to build a fort came from trees that died 600 years ago, then the fort was probably built 600 years ago. Compute the matrix e power at if the matrix has the form various various matrix to plug into for a equal to 0 1 0 0. So here and that changing where in the showing the result e power 1 comma 1 g 1 0 then e power x equal to x power 0 x power 1 x power plus 1 by 2 x square plus 1 by 6 xp plus up to plus 1 factorial x and plus exponential pi of phi equal to pi of whole 0 pi of phi power 1 1 by 2 pi of phi power 2 plus 1 by 6 pi of phi power 3 plus up to plus 1 n factorial pi I power n exponential 314 159 265 314 159 2 power 265 power 0 here 1 power here 1 by 2 power square 1 by 6 that matrix power 3 plus up to 1 n factorial that matrix power n then value. So here got this result. So got this value. Okay. So here e power 0.5 3 1.0 minus 0.05 into 2.10 got minus 1.04 0.62 minus 0.21 minus 0.84. In textbook progression, definition, theorem, proof, then examples. Versus discovery progression, specific problem, general problems, then helpful concepts, then definition. So, among the